So, I will continue discussion on graph plotting, as well as today I will discuss about the calibration. So, for graph plotting I have discussed that how to plot a graph on a graph paper. So, this is the basically manual plotting and same way actually we use the graphics to plot the graph. So, today I will discuss what is the advantage we can get from graph plotting, as well as how we can extract the information from the graph. So, actually this on same graph sometimes we plot few sets of data. So, from that one can compare with one with other, and directly you can see this change of how they are different. So, just I will show, I have one plot from my lab, I will show you this basically for comparison, this type of graph we plot. So, here you forget what is this zinc, cobalt oxide etc., this you forget. This is just one experiment we did and this we plotted. So, just I copied and taken here to show you. So, basically just here you can see this axis is x axis is growth temperature and y axis is solubility limit. So, this is similar as say what is the solubility limit of sugar in water. Now, that if you want to study at different temperature, so solubility of sugar in water, it will be different at different temperature. Okay. So, if you take this example, so this whatever here I am showing this similar to that. So, so this growth temperature whatever this say it is a water temperature, and this whatever here I am showing this 4 types of sample. So, one you can take as a, so this 4 type of sample I have taken. So, you can take one is salt, another is sugar etc. So, 4 types of solid you can take and put in water, okay. And this water you are keeping at different temperature and finding out the solubility of different solids. Okay. So, here these 4 types of solids we have taken and we are finding out the solubility limit at different temperature. So, solubility limit maximum how much the solid can be resolved in the liquid. So, that we have plotted. So, this is, so there are 4 plots, and in this type of graph basically we use separate different legends, different symbols. Okay. So, one symbol we have used this circle and this star, then triangle, this then square. Okay. So, if you want to compare similar type of data, okay. So, then we put them in, we plot them in same graph, and for that you have to use the different symbol, so that one can understand this that they which lines or these sets of data for which sample, and that also you have to mention here. We have mentioned this circle for this zinc cobalt oxide, then star for zinc manganese oxide. So, in your case whatever example I gave you, so that we have to write the circle for sugar, star for say salt, etc. Okay. So, this graph, as I showed this, so graph paper is used, or plotting graph is used to compare the similar sets of data, and how the solubility limit here is changing for different samples, directly you can compare. You can compare that this the solubility limit of this one, this here zinc nickel oxide. So, basically in zinc oxide we are putting different transition metals. Okay. So, cobalt, manganese, iron and nickel. So, how much cobalt can be resolved in the zinc oxide? It is a zinc oxide, you can think that it is the water, and cobalt, manganese, iron, etc. you can think as like sugar or this the salt, etc. Okay. So, this we are so solubility limit of these elements we are trying to find out at different temperature. Okay. So, from here directly you can compare, okay, solubility limit of nickel is the minimum, okay, and then this it's the I think about this is 3%, and this one is for iron. So, it's the 20%, and star one is manganese. Okay, star one is manganese. So, this both manganese and this cobalt both solubility limit is 30%, and with temperature how solubility limit are changing for different elements, that directly one can compare. Now, these 4 sets of data, you have 4 sets of data on a table. So, from table it is difficult to interpret, okay, but if you plot them, so it is very easy to compare. So, this is the advantage of this plotting graph, and and one has to decide that how we should represent this data on a graph. Okay. So, if you plot again using different 4 graph paper for 4 sets of data, so then again it will be difficult to compare. So, if you put them on the same graph using different symbols, okay, so easily one can follow these 4 sets of data, and it is the this difference among them is very visible and is very clear. Okay. So, this the way we can interpret data using graph paper, okay, or plotting graph. So, next I will show this another type of plots. Here again I have basically 4 plots. This is one plots, then this is another plots. So, this third one and this is fourth one. Okay. Here what we have plotted? Here you can see we have plotted basically magnetization as a function of magnetic field. Magnetization as a function of magnetic field. So, this also again data from our lab, and that just we have taken from our paper. So, this we have measured in our laboratory. So, magnetic material. So, basically this material was I think it was I think it is a ferrite material, whatever the material, forget it, but we have measured the magnetization of a magnetic material as a function of magnetic field. Okay. And here 2 plots you are seeing, that is basically same sample, but this sample was prepared at different temperature. One was at 300 degree centigrade, another is 600 degree centigrade, and other say here 350 degree centigrade, 650. So, 2 types of sample, same sample, but it is annealed. Okay. It was prepared in 2 temperature. Now, we want to see the difference, what is the difference in magnetic property of this two growth temperature. So, here we have plotted these two sets of data. So, you can see one is closed, this one is solid circle, another is open circle. So, here in all these cases you can see there is a difference. So, here directly again we are plotting these two sets of data in same graph. Here basically you can think that this is a one graph, this is second, third, fourth graph, but again we have plotted on same graph paper, and this graph paper was divided into 4 parts. So, each part is used for a plotting of two sets of data. So, here also another advantage that all of them you are putting on the same graph, but this time it is slightly different that instead of 4 graph paper you have used 1 graph paper, and that in that graph paper you have taken these 4 regions for plotting 4 different samples, and for each samples again 2 sets of data. So, that is what we have present lot of data on the same graph paper. So, here one is that for comparison how many sets of data we are plotting on the same graph, this is one information. Second information is that in each graph you see we have another small portion, this another graph you can see, another plot you can see. This basically we tell this is the inset, we tell this is inset. Here basically from this graph, so for magnetic metal, generally ferromagnetic metal you get MH loop, hysteresis loop, from hysteresis loop what you want to know? You want to know what is the coercivity, what is the remanent magnetization, what is the saturation magnetization. Okay. So, this information we want to know from this graph, but in all cases problem is it looks is not a hysteresis loop, it is just a line. Okay. So, that is because of this scale, this range of this field is huge, and because of that this all data are squeezed. So, basically now you have to expand, you have to magnify it to see whether they are passing through the 0 or they have some they are cutting x axis and y axis at different points rather than the 0. So, that points is basically will tell you about the coercivity and the remanent magnetization. So, so you have to magnify this portion. Okay. So, that is what we have done here. So, here range is minus 5000 to plus 5000, more than 5000. So, here just minus 55 to plus 55 means very small portion, this portion we have magnified. So, this magnified portion we have plotted here. Okay. Magnified portion we have plotted here, and you can see clearly no, it is not single line, it is not a line passing through the 0, it is not a line passing through the 0, but they are passing, they are cutting this y axis at this point and x axis at this point. So, this is the coercivity. So, and this is the remanent magnetization. So, you can find out the value of this coercivity and remanent magnetization. So, it is not here important this how to find out coercivity and remanent magnetization, but this is just one example I have taken. So, this is the way to find out the information from the plotting graph, and just plotting graph is not enough. So, you have to know how to extract the information, and for that what you have to do. So, this is another type of use of the graph paper to extract the information. So, next another example I have taken here. So, here what we have plotted. So, here basically this is again from our lab, this data we have measured the magnetization of a magnetic material as a function of temperature. If you vary the temperature and measure the magnetization, and then we have plotted here. So, here what we are seeing, this curve is like this, means change of magnetization with temperature. If you start from higher temperature 300 Kelvin, it is basically room temperature. So, then this magnetization is around 45 EMU per gram, whatever the value. So, now it is changing, suddenly it drops, then suddenly drops, then it changes like this, okay. That changes like this, okay. Then again it's become flat, okay. So, this type of change. So, this magnetization as a function of temperature, this experiment we do to find out the transition temperature, Generally in magnetic material there is a transition temperature. Below that transition temperature it may be the ferromagnetic or antiferromagnetic, and above that transition temperature it is paramagnetic. So, what is the transition temperature if you want to find out? So, this ferromagnetic material, this it has in ferromagnetic phase it is a higher magnetization, and this magnetization changes with temperature, okay, it decreases, and then it suddenly drops towards the 0. Okay. So, then when this so this basically what is happening, the ferromagnetic phase it is getting changed to the paramagnetic phase. So, at what temperature this basically this change occurs, or this change is completed. So, that we can find out from the change of curvature of the curve. So, there is a inflection point where basically this curvature changes. So, here you can see this is one curvature, okay, and this is another other side curvature. So, this curvature here like this, okay. So, radius of curvature is this, and here this another curvature, this another curvature, here another curvature, here is another curvature. So, here it seems that so there is basically slope, there is a certain points is called inflection points, and there this its slope changes, sudden change of slopes from positive slopes to negative slopes. Okay. So, so this point is taken as this inflection point is taken as a transition temperature. Okay. So, so one can guess that here there is a transition here, and there is a small some other kind of phenomena here. So, so how to find out this transition temperature? So, generally from here you can tell, okay, this is the point 250, around 250 or 260 is the transition temperature. So, from here also generally we take this middle point and tell, okay, this is corresponding, this temperature is the transition temperature. But if you want to find out accurately, and you know that that will be the transition temperature where the slope is suddenly changing. Okay. So, slope means you see this dm by dt, right, that differentiation of magnetization with respect to temperature. So, dm by dt. So, that is slope. So, now if I plot dm by dt versus t, then basically I am plotting plotting slope as a function of temperature. So, how slope is changing as a function of temperature. So, this we have plotted here. So, dm by dt as a function of temperature. Now, here you can see this the change of slope is this, as I told, from positive to negative or negative to positive, this change, sudden change, that the inflection point, and that is the transition temperature. So, here this change, slope change is prominent. Here is difficult to tell the exact point where the slope changes, means sign of the slope changes, but from here clearly you can see this the here this changes, and this temperature is around, accurately you can find out is this 250 or 255 or 252, okay, accurately you can find out. So, this is another tricks we apply to find out the information. So, in this case we want to find out the transition temperature, and we know this which point would be the transition temperature, that is the inflection point, and inflection points where the just sign of the slope changes. So, it is better to plot the slope as a function of temperature, so that you can find out from this your original data, and from this plot you can find out the transition temperature accurately, but from this graph it is difficult to find out the exact accurate transition temperature. Okay. So, this is another use of the graph, plotting of the graph, okay, plotting of your data on a graph paper. So, and similar another example I have here, we have another data is because they are slightly complicated, two transition kind of things are there, but now aim is not there to discuss the physics, but I am discussing about the utility of the graph. So, here it is clear, you see this just this slope is 0, here also slope is 0. So, in between this slope changing. Okay. So, that means this type of variation is tells. So, here this basically this radius of curvature is this side, and here radius of curvature is this side. Okay. So, there is a change of curvature. So, exactly what is the inflection point here. So, it is very difficult to find out the exact inflection point, but generally we take this middle point of this, but so that is it may not be accurate. So, again if you take this the derivative of this y axis as a function of x axis, then here, so that derivative we have taken of this curve, and here you can see that this change of slope, change of sign of the slope is you can find out here. So, from this plot accurately you can tell what is the temperature, it is a 36 in accuracy of 1 Kelvin even, yeah. So, but here it is it from this graph what is the slope, what is the transition temperature, it will be accuracy will not be as you find out from this derivative. So, here there the uncertainty will be more, and here it is very precisely telling this exactly what is which temperature is inflection point, and that is the transition temperature. So, here basically if we have measured magnetoresistance, we have measured magnetoresistance as a function of temperature. Okay. So, if we apply magnetic field this on a material, and if we measure the resistance, so resistance of this material changes with the magnetic field. Okay. Now, if you use a particular magnetic field, at that magnetic field whatever the magnetoresistance, now that magnetoresistance how it is changing with temperature, that is what we have measured. Okay. So, this is one of our sample. From that on that sample we have taken, we have measured. This is again from our lab, okay, and we have plotted and got the information from this. So, this again some transition here basically this is a higher resistance, this is lower resistance. So, insulator to metal transition. Okay. So, electrical transition is there, it is just similar to magnetic material, ferromagnetic to paramagnetic transition. In this case insulator or metal to insulator transition when you are coming down from room temperature to lower temperature. Okay. So, this is the example of utilization of the graph to find out your parameter, whatever your purpose of doing the experiment. So, that you can get from the plotting graph, and basically for analyzing the graph. Okay. Analyze. So, this is the way to analyze the data using the graph paper. So, I think there are many examples I can give, and same graph can be used for two ways. You see here these two axes basically again magnetization as a function of temperature. Okay. So, this part is plotted as a magnetization as a function of temperature, but other part is plotted as a this 1 by chi versus temperature. Okay. So, what is the reason that I will not tell now, but this is the this relation, you know, this is the relation for this is the Curie-Weiss this is the Curie-Weiss it is called I think Curie law, and it is the Curie-Weiss law. Okay. Curie law is basically for paramagnetic, and Curie-Weiss law is for ferromagnetic material, but this theta here basically this is also for paramagnetic phase, but that is this equation is valid only above theta, t minus theta. So, this theta is basically some transition temperature. This so it is you can tell it is T c, T minus T c. So, this expression is valid, otherwise it will be negative, because if T is less than T c, then it will be negative. So, then it is not valid. Okay. So, this expression is valid only above T c, only above T c. Okay. So, above T c it is paramagnetic phase, below T c, below theta it is ferromagnetic phase. Okay. So, since this equation is valid only for paramagnetic phase, and I have opportunity here, you see, if I plot chi versus T, and chi is nothing but m by h. Okay. So, measurement we have done m versus h. Now, m versus T applying a particular field. Now, you divide this m by that magnetic field, then it is chi. Okay. So, this chi is inversely proportional to the temperature. Okay. So, it is the if you plot it will be I think hyperbola, this curve will be hyperbola, but if we plot 1 by chi versus T, so they will be linear, their relation will be linear. So, and always when we plot, if we have opportunity, so we try to get linear curve. So, instead of plotting chi versus T, if we plot 1 by chi versus T, then you will get a linear curve, and then it is easy to interpret it, because in this case if you just it is easy to find out the slope of this line. slope of this line. If you find out the slope of this line, then you can get this value of this constant C, this Curie constant. Okay. So, but if you plot chi versus T, then it will be hyperbola curve, and from hyperbola curve it will be difficult to find out this C. So, to extract information, so you have to apply tricks, okay, in plotting. So, you have to decide whether I should plot chi versus T or 1 by chi versus T, okay. And in this case here that magnetic metal you have taken and doing experiment measuring magnetization as a function of temperature. So, some portion this below Tc it is ferromagnetic phase, and in ferromagnetic phase this 1 by this relation is not valid. Okay. So, but in this case representation magnetization versus temperature is good enough, because this variation is this like this, magnetization changes and it goes towards 0. Okay. That means that is the transition temperature, it is going towards the ferromagnetic phase, paramagnetic phase, and in paramagnetic phase this, if you plot 1 by chi versus T, then it should be straight line. So, directly you can also, if you know the nature of the curve for your from theory, so then plotting your you should plot your data accordingly, and then directly from seeing the curve you can tell about the nature of the magnetization. Also you can find out the some parameters, as here one can find out the C. Okay. So, these few examples I showed you how to plot, what information you will get, and how to extract the information. Okay. These are the in general I discuss about the utility of the graph, how to plot graph, and how to get the information. So, I think that is enough for you to do your experiment in lab and get the information. So, I think I will stop here and I will discuss calibration in next class. Thank you.